there are a lot of reactions that you have in a typical reaction mechanism. And sometimes it's not really possible to take all of those reaction rates and all of those reactions and solve for them, especially when you're trying to do something like a CFD simulation, right? For an engine or for a gas turbine, which are sort of huge devices. So in all such cases, what we typically do is that we simplify the mechanism, right? And there are two levels of simplification. One level of simplification is to simply come up with a one-step combustion mechanism, which lacks the physics or lacks the understanding of what is happening, and it is simply a good empirical fit, right? It is simply a fit to experimental data, and it works within the set of conditions for which you have experimental data. Outside that, it will not work. The other option is to make a set of simplifying assumptions, right? Such as saying that, okay, a reaction will progress only in the forward or backward direction, or by making an approximation on a species and saying that it's at steady state, meaning its formation is equal to its consumption, or saying that a reaction is under partial equilibrium. So these are two options, and we discussed the first option in the last class. We said that, okay, one way of coming up with a one-step mechanism can be you just write down the fuel plus oxidizer and the products, and then uh, by measuring the consumption rate, by plotting how a particular reactant is getting consumed. So you have the reaction progress or time on the x-axis, and you have the concentration of one of the fuels or the oxidizer. So typically we are tracking fuel. So let's say CH4 is the fuel, and you're tracking it, and you measure how it gets consumed in a burner, in any other kind of flame, and by measuring its rate of consumption, we are able to come up with this expression. And by doing a good by just fitting the data, by just fitting the experimental data, we get numbers for the activation energy, the pre-exponential factor, and also these coefficients, right? And so essentially, what we are doing is we are coming up we are basically coming up with an expression which looks very similar to the rate law. And the thing is that as we said for the rate law, the values of P and Q are not the same as what you have in the stock, are not equal to the stoichiometric coefficients, but they are determined experimentally. And so this will work only in a certain range of conditions for which we have experimental data. Okay. Now, what we want to cover today is to look at a rather simple mechanism and see how we can come up with a one-step version of it uh, by making simplifying assumptions, right? So we will make three simplifying assumptions here. Basically we'll make an assumption about the fact that one of the species is at steady state, right? We'll make an assumption about partial equilibrium. A particular reaction is at partial equilibrium. And we'll also make an assumption on the directionality of a reaction, meaning we say that, okay, a particular reaction will only happen in the forward direction or in the backward direction. Okay, so we'll apply that, and we'll see how we can come up with a simplified version. Now, the difference between this simplification, where we apply some approximation or we make some assumptions, and the previous one is the fact that this one is based on actual physics. So as long as your assumptions are valid, the expression we derived, which again can be as small as a one-step reaction, is valid. Okay, so that's the main difference. This one is more physics-based. It's a more scientific way of let's say coming up with a reduced mechanism for any species or any molecule that is being formed. All right, so here we'll do that with an example for the formation of NO, which is nitric oxide, and it is one of the, let's say, main pollutants in combustion. All right. So let's start by looking at this steady state approximation again, what it means, and then let's start by talking about the formation of nitric acid. Sorry, nitric oxide. So when we say the steady state approximation, we typically apply the steady state approximation to very highly reactive intermediate species, right? And it's a reasonable approximation because when we're dealing with very, very highly reactive species, radicals and others, they tend to get formed and consumed very quickly. So essentially, the rate of production is equal to the rate of consumption. Or you could say that as it gets consumed as quickly as soon as it's formed, right? So their more or less their concentration remains constant. It's going to be very small, and it remains constant. It does not change over time. So if a concentration of any particular species is almost constant, then we can say that species is at steady state. Or in other words, as we discussed here, the net production rate is zero, or the production rate is equal to the consumption rate. And now let's look at how we can apply that for coming up with a simplistic version of the mechanism for the formation of nitric oxide, which is NO. Now, if you were to look at how nitric oxide is formed, you can simply write this equation, N2 plus O2 giving 2NO. Now, when we look at this equation, the first thing that comes to our mind, or when you look at the heat of the reaction and other aspects of this chemical reaction, one thing that's obvious is that it's a very endothermic reaction. So this is not something that's going to take place at atmospheric pressure, right? So at low temperatures, at atmospheric conditions, atmospheric pressure and temperature. So pressure is fine, but at low temperature, ambient temperatures, it's not going to happen. It happens when the flame goes to when you're dealing with very high temperatures, right? And so till now, till chapter 2, when we were writing the chemical reaction equation for the oxidation of any fuel, let's say again CH4 for simplicity. So when we wrote CH4 plus 2 O2 plus 3.76 N2, we just wrote the products at CO2 and H2O, right? CO2 plus 2H2O plus we said that nitrogen does not react, and we assumed it does not react, and we wrote it as 7.5 to N2. Whatever you had on the reactant shows up on the product. But this is not true, right? This was a simplifying assumption, and the fact is, at high temperatures, the nitrogen that we have within that comes from the air, basically, it does react and it forms nitric oxide, which is which is one of the toxic pollutants, right? It is something for which we have a criteria. When we talk about emission criteria, right? So for every device that you have that burns fuel, whether it's a car or it's a furnace, it's a boiler. They are supposed to follow some emission guidelines, in the sense that that burner or the car or any other combustion device should not emit more than a certain quantity as described by the legislation or by the government authority. So nitrogen oxide is something that has a number associated with it, right? So it's a very important pollutant. It's formed always at high temperature. So now, if it's so important, it's equally important to understand how it works and how you can, what are the key reactions in its formation, so that either you can minimize its formation, or you can come up with some other radical or some other chemical to, let's say, break the chain that leads to the formation of NO. Okay, so this is the basic idea why people are interested in nitric oxide. So in a simplistic manner, you can simply write N2 plus O2 is going to give you 2NO, right? And this reaction itself, as I mentioned, it's very highly endothermic. It cannot happen at ambient conditions. It needs very high temperature. But when you look at, or when you measure the amount of nitric oxide that's formed in typical flames, right, at high temperature, it's difficult to justify that this sort of reaction is able to produce the large amount of NO that we are able to see, right? Because if you look at this reaction itself, nitrogen plus oxygen, this reaction, yes, can produce NO, but here we are dealing with two stable molecules. Okay, so breaking them and forming nitric oxide, it's not a very fast reaction. It has a very high energy barrier that it has to pass through, because you're talking about breaking the nitrogen bond, and nitrogen has a triple bond. Okay, so the more the bonds between the molecules, the more difficult it is to break. Okay, so this reaction itself is not going to happen as it is. Nitrogen and oxygen are not going to collide and give us 2NO directly. And so then the question in the community or in the combustion community was to try and understand how is it actually formed, because they were not able to explain the amount of NO being observed from flames uh, physically or from the chemical point of view, looking at the simple reaction. And so Zeldovich and his co-workers, he came up with a mechanism. He said, look, it's not a one-step reaction, it's actually a multi-step reaction. Okay. And what's actually happening is the nitrogen molecule is initially being attacked by oxygen atom. Okay, and this oxygen atom is simply produced in the flames, as we saw in the previous reaction, previous classes about chain initiation, chain propagation, and so on. So it gets produced in one of those steps by dissociation of oxygen or by radical attack on the oxygen molecule. And once you have this oxygen molecule in here, the oxygen molecule, oxygen atom in here, once you have the oxygen atom in here, this oxygen atom, which is of course very reactive, it's not a stable molecule, this oxygen atom then attacks the nitrogen molecule. Okay, and even though the nitrogen molecule has three bonds, right? It's a triple bond. It's very strongly bonded. The oxygen atom is reactive enough to break that bond, and it forms NO, which is nitric oxide. So 1 mole of nitric oxide plus 1 mole of nitrogen atom. And now this nitrogen atom that's essentially formed here, this is also a radical. It's also very reactive. So then this goes and attacks an oxygen molecule that's available from the air as part of the air. And oxygen molecule plus N then gives us another molecule of nitric oxide plus another oxygen atom. Now this free oxygen atom, it can go back and take part in this reaction here, or it can also, go and attack other fuels and be a part of the overall combustion reaction. But essentially, what you see is here is a chain sort of getting started, right? So here, this N2 plus O giving NO plus N is a chain propagation. You have one radical on the reactant side, one reactant on the product, one radical on the product side, and same is the case with Z2, right? And this is so when you put these two reactions together, N2 being attacked by oxygen atom, forming 1 mole of NO, and then the nitrogen that's formed in here attacking an oxygen molecule and forming another NO plus oxygen atom. These two reactions put together are able to explain the amount of NO that you see from combustion. So essentially, once this was done, it became clear that okay, N2 and O2 cannot just attack, cannot collide and themselves form NO, 2NO, 2 moles of NO. Is just too slow for that to happen. And the way it's happening is basically through these two steps, right? And here, essentially, when we look at these two reactions, you can think of them as these are very good examples of consecutive reactions, right? So we said consecutive reaction is one where you need a certain molecule or certain atom to form, and then that leads to the formation, its consumption leads to the formation of a final product. So in this case, in the first reaction, we are forming NO plus N, the nitrogen atom. This nitrogen atom that's forming, it's actually going and attacking the oxygen molecule, and it's then completing the reaction by forming the other molecule of nitric oxide. So whenever we are dealing with such reactions where the first reaction Z1 has to happen for the second reaction to start, the rates of the overall reaction starting from N2 plus O, giving NO plus O, or starting from N2, the oxidation of N2 to give us 2NO, is limited by the rate of the slowest among these two. Okay. Now, when we look at these two reactions, in the first reaction, oxygen atom is attacking nitrogen molecule, and as I said, nitrogen molecule has a triple bond. Okay. Now, in the second case, nitrogen atom is attacking an oxygen molecule. Oxygen molecule has a double bond. So the more the bonds, the more difficult it is to break. So and the more difficult it is to break, the slower the reaction is. That's how basically it all works. So when you look at these two reactions, Z1 and Z2, the reaction Z1 is slower. And once the reaction Z1 completes and you form NO plus this nitrogen atom immediately attacks an oxygen molecule, and it leads to the formation of another nitric oxide molecule plus oxygen atom. So as soon as Z1 is done, Z2 occurs almost spontaneously. Okay, so we can more or less say that this reaction, when we look at these two reaction steps, it's more or less dominated by the reaction Z1 or the rate of reaction Z1. And these two are basically essentially the reactions that we see in most conditions. But if you sort of go to more, let's say, fuel-rich conditions, then another set of reactions may also become more important, such as the Z3 mechanism that I'm showing here, where the nitrogen atom form in Z1, it has the option of attacking O2, but it also has the option of attacking the OH radical. And once it does that, it forms H plus NO, right? But either way, NO is being formed. And nitric oxide is essentially the pollutant that we are after. So now, when we look at this overall setup, what we essentially are trying to do is we want to come up with a simplistic expression for the formation of NO, right? And we want to do that in terms of its basic molecules, which is N2 and oxygen. Okay, so essentially what I want to do is I want to write something like the rate of formation of NO by dt is equal to some rate. Okay, let's call it I don't know, K alpha, right, or something, some reaction rate coefficient times concentration of N2 times concentration of O2. Both of these raised to maybe some coefficients, P and Q. We don't know what P and Q is, right? I just want to come up with a simplistic expression, okay? Just like we did for the one-step mechanism. The only difference is when we did this for one-step mechanism in the previous class, when we described that, it is based only on experimental data. There is no physics involved. But when we will come up with some really simplistic one-step equation to describe the formation rate of NO, we will come up with a more, let's say, we'll come up with an expression which has more physics involved and which is valid when all of these assumptions that we speak about, the three assumptions that we'll speak about, as long as they're valid, this equation is valid. It is not limited by any experimental data. It is simply limited by the conditions under which the assumptions are valid. Okay, so that's what now we will do. We'll start by applying assumptions one by one, and we'll eventually come up with some sort of an expression like this at the end of this exercise.